Okay, good morning. Let's start on time, so we'll get lunch on time as well. So my name is Eric Vink. I am coming out of Belgium, from the French-speaking part, as you can guess from my accent, even if my last name is more coming from the North Dutch part of Belgium. I've got here a box of chocolates. That's for you after, but also if you have any questions or comments, you will get one chocolate, or two. Or 6, right? Because you are now on IPv6 here. So, objective, that's an advanced session, so I will assume that you know about IPv6, what is a route advertisement, what is IPsec, how it goes. I will give you no details on this. Also, there was a big tutorial of 4 hours about security on Monday afternoon. If you were that Monday afternoon in the room, I strongly advise to leave this room right now, because this 2-hour session is basically the 4 hours shrink to fit within 2 hours, and a little bit more advanced. Okay, so as usual, if you are following the slides on the PDF, I have more slides in the PDF than here. For the sake of time, I'm skipping a couple of them. Also, there are slides with a small blue book on the top right. It simply means that for your reference, I will not go in much detail during the explanation here. The kind of stars points you to other session, either on Cisco Live Online, or you can get access, or this week. But as we are already Thursday, it's a bit difficult to go back in time to attend a session on Tuesday, obviously. And a few of them as well with this kind of lab engine, meaning that when you see this slide, and I describe our experiment, don't do it into your live network. Do it in the lab, basically. Now, you will understand why, pretty obvious. Cisco WebEx team. Obviously, I'm here. I'm not behind my screen right now, so I cannot answer your questions on WebEx team, but do it, and for 2-3 weeks, I will still follow up. Okay, then after, I will stop, obviously. IPv6, we are transitioning to it. Right? Slowly. But think about it. We are used to it. At my first job, it was the car I was driving, a Peugeot. Now, I can rent a plane and fly it. Or, at my first job, what I was doing, maybe some people remember, those kind of MAC address, it was using DECnet, right? Before IPv4 even, right? And you even see the 100 here. It's actually in the MAC address. This is the 64, which is here, long time ago. You need to have gray hair to remember this. And now, where are we, or where are we aiming to go? It's obviously IPv6. And you know, if I'm using ::1, my split node multicast is this one. And again, same thing, we put the one here, is the one coming here. The split node multicast is mapped into an Ethernet multicast for the same thing. Why am I explaining this? It took me 85 hours of supervised flying to be able to fly a rented plane. This one is taking way more years. Okay? But something important, I still love to learn, and I still get fun doing deploying V6 or learning to fly. In this room, that's the red part that's important. You need to do it securely, meaning that when you deploy your V6 network, you need to do it in a secure fashion. You are here, that's a good point. Agenda. Quick introduction to a tool we will be using, that I will use extensively in the lab. It's called SCAPI. We talk about, in extent, more about 1 hour most probably, about LAN security. We know in IPv4 dynamic app inspection and DHCP snooping, we need to do the same thing in IPv6. That's basically it. Extension headers, they are really annoying in the world of IPv6. There's one way to keep the internet changing and evolving, though. So those are important. But on security aspect, they are pretty bad. We will spend a lot of time there. Dual stack and tunnels, that's one preferred way to deploy the network. they have their own security issue as well. Oops. A few words as well on telemetry. How can I feel what's happening in my network? In short, NetFlow still works in IPv6, oh, that's good. Forensic, I got in my logs a v6 address, and I need to know where this IPv6 address is. Who is the guy behind, or the device, or the printer? How can I find it back? That's also very different. That's the reason why we talk here. Quickly, a few snapshots and ideas about the Cisco product that can help you to deploy securely a v6 network, and a summary. Interrupt me at any time. You will get a chocolate, and maybe this will be more interactive and more interesting for everyone. Scapy. Scapy is a tool written by two French guys in Python. And just a few explanations. Scapy is a very complex tool to use. Very powerful, but complex. It took me, every time I do it after 3 months, it took me about half an hour to remember everything. And I've used it multiple times. So basically, it's an interpreter. You can assign, it's basically some kind of Python, right? It's actually Python here. Target like a variable, and you can assign a string. So far, so good, it's easy. Second one, I want to assign to the variable packet something to build, byte by byte, a packet. And that's very powerful here. IPv6 here will create a 40 bytes IPv6 header with most of the default, most of the field having a default value. Up limit, for instance, 64, destination, your own address, source, your own address, and so on. In this case, I specify that the destination is target, right? The value I just assigned above. Then I use the slash. Slash in this context is about concatenating headers, okay, and values. So this after my IPv6 header, I am creating an ICMPv6 echo request header. And again, default value, but here I selected, for instance, an ID 1234 and the sequence number, a random number. After, last thing I'm doing, SR1, send and receive one packet. So I'm transmitting the packet and I'm waiting for a reply. And the reply is here. You see, echo reply. Very, very powerful. You can put every field to a specific value. You can even build illegal packets if you want, which is useful for testing device. Okay, that's basically what I just explained. So when in 1 month you will want to try it, you remember vaguely what I just said. And let's go. Let's dig into the LAN security issue. And the very first major attack, the one that has prevented many v6 deployment, is the rogue array. You remember route advertisement, router solicitation. Route advertisement are sent by valid routers, but can be sent by anybody, like the bad guy which is coming here, with the black hat, of course, right? So he's sending a rogue array. The machine on the left, the PC, believe it, and we will see in the demonstration. So now he's sending all the outbound traffic to the MAC address of its default router, even if the bad one. Then this one can do a DOS, blocking the traffic, obviously, or basically do a man-in-the-middle attack. Okay? We all know this. There are attack tools for doing this. Just want to repeat again, this attack works fine on your IPv4 only network. What defines an IPv6 network is not a v6 enabled access point, a v6 router, or a v6 switch. No. What defines an IPv6 network is having nodes like Windows machine, like Mac or Linux machine with v6 enabled by default. So this attack works on any network. Okay? Okay, how can we do it? First one, what we call host isolation. This one works all the time. We simply prevent, by using private VLAN, or if you have Wi-Fi access point, what you call isolation mode, where basically no two nodes in the same LAN can talk to each other. They can only talk to the router, and that's enforced at the layer 2. So now we have the router on the top. We know where it is, on which port, and we know on other ports are only clients. So we can configure them later. But as we know this one, when it's sending its array, we know it's a promiscuous port. So basically, it's flooding the array to all the other ports in the same VLAN. Then the hosts are happy. The Black Hat PC wants to do the same. It's sending its rogue array. That's a device, that's an isolated port. It's only sent actually to the router, not sent to the other one. That's very strict, okay? Host cannot send anything to other hosts. So they can send no attack, basically. So far, so good. Now think about this. Can you do it all the time? Yes and no. Because with this, duplicate address detection does not work. If two machines of there are configured the same v6 address, they will not detect this. Not good. Now think about, can you do it with IP phones? So you can get no connection between two IP phones? Yeah, not that good either. There are ways to go around this by playing with the L bit on link prefix, yes or no, forcing all the communication to go to the router. So that's doable if you want to get voice over IP anyway. A better way is what we call array guard. And the attack and the protection and the mitigation technique has been defined in an NRSC. And again, it relies on the fact that as network operator, you know where your clients are and where your trusted router is. And you configure different settings for the clients and a different one for the router. And we'll go a little bit more in detail later. You can do it with an access control list, where typically you will apply the access control list that blocks all the route advertisement. Those are ICMP, so that's kind of naively easy to do. Again, it's more to come. Or you can apply the CLI, and I shall come back on the CLI later, where basically you define two policies, one for host, one for routers, and you apply the policies for host to everyone in the VLAN, and a more specific one to the port where the router is. Same thing after. The router is sending its route advertisement. Yes, device role is router, can go and be multicasted on all the client ports in the VLAN. The other way, the bad guy wants to send an array. Guess what? Device role is host. It's blocked, okay, and even locked. So we are all set there. Now, let's dig a little more on the CLI associated with first hop security. FHS here means first hop security. That's basically how we stop all the attacks at the first hop, so within the LAN. So each feature, we can attach them globally. If you type it at the CLI at the top, global level, we can apply it on the VLAN level, and we can apply it as well on the port level or the interface level. The more specific one wins. Okay? If you configure policy red globally and green on the interface, for this interface, there's the policy green that will be enforced, of course. It does make sense. There are multiple features in the pack of first hop security. There are array guard, we shall see later device tracking. Each of these features can have different policy level per interface or per VLAN. Okay? We configure them completely differently. Different CLI, so you can mix and match. For instance, here you see the array guard. We have attached policy host to the complete VLAN and attach a specific router on the internet. And on the VLAN itself, we configure another policy, device tracking. This device tracking will apply to all nodes in the VLAN, including the fast Ethernet that's there. Okay, I simply repeat, again, for your consumption when you are back at home, that's what I said. You even have example here. Booklet on the top right, I'm skipping it. Okay, we will see more example coming from. Something important, for each feature, specifically for array guard, you will have different device role. You will apply a policy to some specific device role and devices. For instance, host, by default, will receive no router solicitation. So they will not know whether another host in the same VLAN is trying to get an array. That's only one good point. And it will receive only a valid array. So by the way, if you configure, you apply a policy with device role host to the complete VLAN, it will not work. Because the router, which is also in the VLAN, will not receive the router solicitation with this. Just pay attention. Okay? For a router, you need as well to define a device role router. This one will receive all the router solicitation, so it can reply to it. And only this port can send router advertisement. All the other ones are blocked. Okay? So whether you have 1, 2, or 3 routers, you need to apply policy where the device role is router. 2 more things. There is one which is called monitor. Typically, you don't use it. This is where you put an IPS, for instance. It will see all the traffic. Valid arrays, invalid arrays, and all the arrays. Okay? But it can send nothing. And a switch. This is typically when you have multiple switches in your access layer, you trust everything which is coming from there, relying on the fact that the other switch is configured correctly. Okay, that's how it's done. Another one is for device tracking. This is about inspecting no more the router advertisement or the router solicitation. It's more about NS, neighbor solicitation, and neighbor discovery, and neighbor advertisement. So basically, this is the equivalent of ARP. That's when we, each and every node try to understand which is the MAC address of another node. In this case, we have basically 2 roles only. Node, which is by default, forcing all the neighbor discovery message, mainly neighbor advertisement, to be inspected. In this context, inspected means if you are valid, go through. If you are invalid, drop. Okay? And basically, we are only receiving, as we are there, valid neighbor advertisement and valid neighbor solicitation. Switch, the same things before. I am relying that my other switch in my network are correctly configured, and I'm trusting them. Okay. Having said this, let's try to go and do some demonstration here. So on this one, I will demonstrate array guard. We have a valid router advertising a prefix 2001 DB8 cafe. We need coffee in, right, in this morning. The victim, which is the host, and basically the bad guy, villain. I like villain because of the same thing in French and in English. It means the bad guy, by the way. So on the host, let's see the configuration at the beginning. So I look about the prefix, and indeed, the prefix I receive is cafe, so I've generated an address out of this prefix. And maybe you don't know this command, show IPv6 routers. It will display a summary of all the array received. And indeed, yeah, we have received an array from this address, from this router and this link local. By default, the preference field is medium. This is RFC compliant. Now let's go to the VLAN. VLAN is also an iOS router because that's easier for me. And by the way, all of this has been configured with very short lifetime. So you don't wait for array to expire. Okay, I declare I am a router because I want to send route advertisement. I declare my address. I selected here bed, so it's easy to see whether it's cafe or bed, right? Router preference high. I can cheat, right? I'm the bad guy. I say I'm the best router in the LAN. And again, you see the lifetime very short to go fast for the demonstration. Done. Now go back to the host, to the victim. If I now show interface, look, I have the bad prefix. So I received the rogue array, I generated an IPv6 address out of this prefix, Slack, right? It's the address of the configuration. Obviously, I'm still receiving the array from the real router, so I still have my cafe. If I look now on all the array I've received, I see a new one coming from bed, the link local address of the bad guy, preference high, still getting the other one, but medium. So now we need to see which one I'm using. You see, default router is bad. I am in trouble. I am sending all my traffic to the bad guy. Okay, so we need to go to the switch and activate this feature you just learned about, array guard. So for this, we will need to define two policies. So let's go. I am defining a policy called host. With device role host, remember, I will not receive router solicitation from others, and I will receive only valid arrays. I need to define, of course, now a policy for the router itself, device role router, meaning A, I will receive all the router solicitation, and in addition, I'm allowed to send and transmit router advertisement. I am attaching the router policy to the right interface, and I apply the host policy basically to the complete VLAN, in this case VLAN 1. Back to host. Again, the lifetime of all those areas are very short, so things happen very quickly. Now I'm only receiving one array. The other one is expired. You have 10-second lifetime. It's coming from the right prefix, and you see here from the right router. If I look at the interface itself, I only have the cafe name. The bad one, the bad prefix has disappeared, timeout. Okay? And of course, the default router is a good one. Now, if I go to the switch, and now I enable some debugging to see what's happening, right? Again, it's very nice to do it in the lab. I see a few things happening, all the arrays I'm receiving and processing, so let's stop debugging, else we will not see anything. This is the bad one. We see the link local, and we see the action dropped. Because it was coming from a port device role host. They are not allowed to send arrays. On this one, coming from the real one, there is no drop, because it was coming from a port with a policy router. Everything is fine. It's fine, but wait until I talk about extension headers, because then it's a little bit less fun. Okay, neighbor discovery spoofing. App spoofing. Neighbor solicitation, that's a quick refresh, right? A wants to talk to B. I don't know the MAC address of B, so I'm sending basically a neighbor solicitation. Yes? Sorry? Can the bad guy change the lifetime? Of course, it will put a very large lifetime, but when I was doing my video, I did not want to wait until one day. But yes.
This mechanism only protects or is only good then if the lifetime is short, or you're vulnerable for the lifetime?
Okay, so the question, and it's a good point. So what about the lifetime here? So first, I put small one lifetime to go for the demonstration going fast, but the lifetime doesn't play a role. It only plays a role here because the attacker was put before the mitigation technique. Now, if you configure array guard before, it will not go. You got it right. So the lifetime are not, yeah, it's always difficult to see the demonstration how you manage it. Anyway, so neighbor solicitation, right, which is your IPv6 address, or your MAC address for this v6 address, and I reply with a neighbor advertisement. This has been designed RSC 2460. in 1998. Okay? Do you remember when DSNF came with ARP spoofing? 2001. So obviously, the people designing IPv6 neighbor discovery did not think about this. Okay? Mistake, of course, but okay, that's life. So we need to protect. And how we protect, that's basically by discovering all the endpoint real address, what you call device tracking. We have on the left 3 hosts, H1, H2, H3. In the middle, we have a switch with what we call a device tracking on a binding table, which is currently empty. And we may have on the right-hand side a DHCP server. How do we build this mapping between an IPv6 address, a MAC address, a VLAN, and an interface? Because if we have all those bindings, then we can refuse a MAC address coming from the wrong interface or an IPv6 not linked to the right MAC address, for instance, and the like. The easiest way is when H1 is doing that, because it's basically sending its neighbor solicitation from an unspecified source address. We intercept all those neighbor solicitation, and we build the address here. First come, first serve. It's pretty much like there's a CAM table in a switch. Okay. First come, first serve. The first one to try to get this address will get it. It go in the table. Oh, H2 wants to do DHCP. So it's sending a request to the DHCP server, and the reply is coming. In this case, compared to v4, is slightly different because one physical host can have multiple v6 addresses on the same interface. For instance, here, I am sending 2 addresses, A21, A22, so I need to put them both into the binding table. Okay? Minor difference, nothing bad. Now, what happens if I receive a packet that is completely unknown to me? Maybe because I just rebooted and lost all my bindings, or because that's the first time, right? Oh, this guy doesn't do that, which is bad, or doesn't do the DHCP. Okay, based on the configuration of the switch, what you can do is use a specific trick of feature, rather, of DHCP v6 called a least query. You will go back to the DHCP v6 server asking, hey, is this v6 address existing to your list database? Yes, then I insert the binding. If you don't use DHCP v6, you will do a neighbor solicitation for this address, A3, to check whether the node exists as well. And this one will be flooded on all the VLAN, not only to the guy pretending to be it. If you receive 2 replies, something is wrong. If you receive only 1, you put in the table. You can do as well it with static. That's easier, but it's a bit more complex. I can do it for servers, right, typically, for routers. So something important is what we call the preference. Because all the methods I explained there, it's clear that DHCP is more preference than Slack. And if you configure something statically for a server, it has even more precedence than DHCP. If you say, trust always this port, higher precedence. If you are using WPA, in the case of Wi-Fi, the binding to the MAC is important as well. So higher precedence than on a switch without .1x. Okay? That's basically, so for each of these entries, we enter different kind of precedence. This is how we do the gleaning. How do we collect all the bindings? Let's use them now. And how? So I've got a single entry now, a good guy on the left, the switch in the middle, and a potential attacker on the right-hand side, but we don't know. So if we receive a neighbor advertisement for an address A1, which is already in my binding table. What do I do? So is it a known IP? If it was unknown, of course, we simply install it, right? We learn, we glean the new information. But if it's already in the table, we need to check what we call the anchor. And the anchor is basically this. Oops. The MAC address, the VLAN, and the interface, right? This is really where the IP address should be there, anchored. If it's the same, though the MAC has not changed, the port has not changed, yeah, we simply assume that the guy is still alive, and we refresh, because those entries time out, right? Else, we need to compute P, the preference. And we compute the preference of this. Again, based on whether it's a trusted port or something like that. If the precedence of the newly received packets is lower than the existing one, such as we learned this by DHCP or statically, we drop it. If it's higher, we replace. Because maybe this guy was the real server on a trusted port, but it was shut down and somebody stole its address. Okay, by using even, not DHCP, obviously, by using Slack, or pretending to use Slack. No, we need to replace because we know this one is the real guy. Else, so same precedence, same way to acquire DHCP or whatever. We simply check by unicast whether host 1 is still alive on the existing previous anchor. So is it still there? Basically, I'm sending a neighbor solicitation. Hey, are you still there? But unicast this time, right? On one port only. Not the usual multicast on all the ports. If it's still alive, if this guy is still there, we drop this packet there. Else, if it's not alive, it's no more there, this is the guy we change. He moved from one access point to another one, simply. So that's normal, right? So now let's apply it and follow the path in red. So the guy arrived, yes, I know the IP. Is it the same anchor though? I'm coming from another access point, another port in my switch. Okay, compute P. P and X are the same. We learned them by Slack. Is the previous host still alive? Yes. I'm dropping it. Easy. Oops. This. Another one. So in this case, we still have this different anchor, so different way. Compute P. Oh, but this one was installed by static server, and I received this one that pretends to be the address of the server by using Slack. So the priority, the preference of the NA here is way lower than my static configuration. I simply drop it. And the last one is the good one. So actually the guy moved, changed from AP, so the switch received it from AP1 and AP2. So known IP, yes, same anchor, no, I moved. Compute P, oh, both of them are Slack. Compare the precedence, but Slack, so they're the same. Is it on this AP, do I still have on this MAC address the same node and the same IP? No, replace. The guy physically moved to from one AP to another one. Example here to prevent this NDP spoofing. Again, that's when we define policies, typically like node and servers. On server, you type trusted port. You will accept the binding that you receive, the MAC address, the first packet with the MAC address and the IPv6 address. You will trust it. High precedence. Because again, you as a network operator, you know where your servers are. 2, security level. On the server, you simply do glean. Glean means I simply learning about the bindings. This one, inspect, I will learn But if you are violating my existing binding entries, like in the previous slide, I drop the packet. And that's basically the configuration that you can see. Okay, let's have a quick demo again. Same kind of settings, but this time there is no more router, same host, another VLAN, and the server, which is Cafe 80, let's say it's a web server. And this time, to save time, I will simply directly configure the feature. So I go to the switch, and I will configure the device tracking. Conf T, of course. And here, a lot of things. So I'm configuring policy node, device role node, right? I can use which protocol I will use to learn the bindings, DHCP-v6, NDP. You can also type DHCP-v4. It will do exactly the same thing as DHCP snooping in the v4 world. Data glean recovery. This is when, oh, I see a binding I've never seen. How do I test it? Either NDP or DHCP. Remember, it was at the bottom of the slide. In this case, I selected NDP. I'm limiting address count to 10. Inspect here means I will drop packets if they are violating the existing binding. And I'll recheck existing entries every 5 minutes, 300 seconds. That's it. So with this, and in this case, I enable the feature directly. So we apply it completely on the VLAN 1 device tracking node. If I ask to display the device binding, you see it's empty. Show device tracking database, nothing. I've learned nothing yet. Okay? Very small network, not very active. There is no Windows machine sending thousands of multicast, right? So nothing, that's only routers. On the host, which is a router, I do ping to the server. Then, of course, I need to send a neighbor solicitation, neighbor advertisement to get the link layer address. And indeed, I learned that for this v6 address, it is this MAC address. Okay, so far, so good. Go into the device tracking database on the switch. And here we see a lot of things. And you can see when the preference is computed, by the way, with the numbers there. So this one, specifically the global 80. Okay, we got the link address. And you see the ND on the left-hand side. We learn it by neighbor discovery. There are many sources you can learn from. Now, let's go to the VLAN. And on this one, we shall configure the same v6 address as the server. We use a very recognizable MAC address, bad. So we can see it as the bad one, right? It's easy. We disable DAD, because by default, routers do DAD. And of course, if we let that going, the router will not use this address, right? So we need to force the router to do it. And we claim that it's using that server v6 address. I will also debug the neighbor discovery protocol to see what's happening here. Yeah, I know I should learn to type correctly, but okay. Host. I am clearing now my neighbor cache, because I want to redo everything, okay? Like if I was batch joining. Show IPv6 neighbor, which is my neighbor cache, empty. So I need to refill it and send a neighbor solicitation and to get a neighbor advertisement. So I'm pinging the server. Success. And if you look on the VLAN, in all the neighbor discovery protocol debug, you see that it's received ONS. He did receive it. Okay. He even sent neighbor advertisement. So we did what he could do to steal the address. But if we go to the switch and we look into the device tracking database, we see that the existing entry for the server is still there. It's not bad, the MAC address, right? Because it was existing, and we checked whether it was not moving. No, it was not moving. So far, so good. The only thing we got, in addition, this is the link local address of the bad guy. But that's normal, right? The bad guy link local is not spoofed, so it should be there. And on the host, same thing. I have the global address of the server still associated to the MAC address of the server. So there we are completely correct. Right? We have blocked the attack. Okay. So we try to secure, and actually we did it, secure the neighbor discovery protocol by preventing wrong information. But what about availability now? What about DOS? You remember when we do normal duplicate address detection? Okay, I have router citation, array, I got my prefix, I generate my Slack address, but then I need to send a DAD. And the DAD is just a neighbor solicitation, right? There's no magic packet there. I'm trying to resolve my own address. And if this address was used by somebody else, he will reply with a neighbor advertisement, hey, that's me. Then you know I cannot use it. Typically used when you are using static addressing and you put 2::1 in your network, right? They will discover, and the last to come will not use this address, so will not connect. Need fix. Now, the bad guy, of course, can do something bad. So again, same network, but now the bad guy C is there. So router advertisement, okay, I make my address. Then the good guy is sending his DAD, as on the previous slide. But now the bad guy, for each and every DAD probe he sees from an unspecified address, he replies, hey, that's me, hey, that's me. Because typically hosts try 3 times, right? If they're using privacy extension, they generate a random number 3 times, and then they stop. So if he's doing it 3 times, it's over. You prevent the access to the network. Bad. How can you prevent this? Again, device tracking. So host is sending his DAD for the first time, makes an entry into the device tracking binding table. When the bad guy sends, hey, it's me, it's too late. It was already in the table. We redo the check. The mobility, the guy did not move, so we block. We can have the same issue with DHCP, of course. I was talking that the people got the address from the router advertisement, but when you use DHCP, you get it from DHCP. So we have a DHCP guard feature, which is exactly the same thing, right? So we configure a specific role as a server on the real DHCP server or relay. So when the solicit is going, yes, only the DHCP server will get it, and the advertise, so giving you the address, basically is only sent to the right person. And if the bad guy wanted to send the advertise as well, it will be blocked. Same philosophy, right? So that's the reason why I'm going fast on this one. Now, what happens now if somebody in Australia knows your prefix at home, PFX, and is sending packet to A, B, C, D, and so on, right? All the addresses of your /64, and there are many of them. Of course, the router there does not know the MAC address of all those addresses. So it's sending neighbor solicitation again and again. It did it 3 times with 1 second interval, while keeping the packets in core. So, and it's going fast, right? You can enter 10,000 entries. You don't have this in IPv4. Remember, in IPv4, most of the network are /24, so 256 entries maximum. And every router can very easily handle 256 incomplete entries. But 10 million incomplete entries for IPv6, not sure, right? So it will not fly as a DOS. So neighbor cache is completely busy, filled. If you have a real guy that wants to connect a customer of yours with an existing address, table is full. No way to insert the address A. And beside this, CPU is 100%, right? So no time to do it. So it is a big DOS. For this, we have another feature called destination guard. Again, using the binding table. So same as before. So now we do the address gleaning, the HTTP static or whatever. When the bad guy in Australia is sending destination 1, 2, 3, we look whether the address, the IP address, exists already in the table. If it exists, we simply forward. If it does not exist, we assume there's no such host. We drop the packets there. Okay. Destination guard. Now, a couple of caveats on this. All this inspection is done into the central CPU in the control plane. Okay. If this guy is sending 1,000 requests or 1 million requests per second, your CPU will be busy anyway. Okay, so you need to use something like control plane policing. Okay. The other point is that if this host just rebooted, it did not send any traffic to learn the binding, it will be dropped, even if it's valid. Okay, think about it. You have a big DMZ with 1,000 VM. They just reboot. If they don't send traffic, the 1,000 VM that do exist with a valid address, if they don't send traffic out, no traffic will come in because they will never be in the binding table. So just beware of this one. You have many more demonstrations by me and by Eric Livia-Bignoli on the internet. That's basically all the syslog message you can get. Sometimes a bit cryptic, but it's okay. For reference as well, this is where it's available and on which platform. So it's coming, and as well an ACI, for instance, which is quite cool. Okay. Extension headers now. This is one part. Typically, I say that IPv4 security and IPv6 security are identical at 98%. Extension headers are one of those two missing percent. That's really something different. And I do like extension headers because they allow, as I said before, the extension of the protocol. We can add new feature. If you know about segment routing, you have heard about it, it relies on extension headers. Okay, so that's really important. Okay. So extension headers, so far so cool, we can get us. A couple of them, by the way, it's very rare to see packets with extension headers, but they exist. And I can change them. Some of them I can only have once. Some of them I can have twice. And the order of the packets is important. I guess most of you at the university or the high school or whatever, you had to program maybe in C, not only in Python. In C code, if you declare a string of 10 characters, char s 10, you can only put 10 characters, right? Now, if you have the stupid user, you are making your first program, you show it to your girlfriend, your boyfriend, say, hey, test. Look, type something, it will be printed back, right? Small program. If you type 5 characters that go into the string, fine. You type 11 or 20 characters, you put them into a string which is 10 characters in C, you actually go into the stack and crash. I guess all of us have done this. So think about this. I use Scapy to generate a packet which looks valid, Wireshark see it, with many extension headers, right? All the line, one extension header. Okay, this one, 2 hop by hop, could only have 1. Remember what I said with the C string? The kernel received this. It should drop it. But, okay, engineers are human beings, they make mistakes. So maybe it will go in the stack, in the kernel stack, and overwrite. Crashing not a program, crashing the kernel, reboot. Or this one, destination header, can only happen twice. 3 times, same problem. Or this one, routing header, should be just after the hop by hop. It cannot be the last one. What happens? How can we deal with this? And first, we are in 2019, so most of the IPv6 stack has found all the bugs, right? So they will simply drop the packet and log it, so not a big deal. But maybe you still want to protect against it. So one way is to block completely the extension headers. That's a little bit brutal, maybe. Or using device like the ASA or the next generation firewall, using the ASA code anywhere on delay, because there they can block invalid combination. Okay, that's one way, or using another firewall. Still talking about extension headers. In IPv4, if you put an access control list to permit, let's say, SSH and block telnet, it's very easy for any firewall or any access control list to find where the TCP and UDP ports are. Fix 20 byte, mostly always fix 20 byte packets for TCP header and 20 bytes for TCP, so you always know where the ports are in IPv4. Move to v6. Hey, between my blue IPv6 header and the TCP in green on the first line, I have a hop by hop, a routing, and maybe AH, authentication header, right? The one from IPsec. We can still find it. It's slightly more complex because all of those extension headers, all of them is always a byte telling, hey, the next one is routing, the next one is something else, okay? And here, the next one is TCP, for instance, and the length. So when the firewall receives this, it can pass it. Okay? You know the length of the IPv6 header, good. You go to the hop by hop, you know then it can read the hop by hop length, go to the routing, it can now read the routing at the length, go to AH, and so on until he finds TCP, and there he knows what to do. Cool. The only thing quite surprising in this case is that if it does not recognize TCP, SCP, or UDP, the transport layers, or whether it's ERGRP or something, a layer 4 protocol. Let's say that in 5 years, the ITF invent TCP++ with a different number, protocol number, number 6, sorry, random number. Obviously, when you are scanning this, he finds something he does not know, he goes to the next line of the access control list. Okay, he cannot search for port because there are no port there. This scanning has got 2 limitations. Obviously, it takes CPU to do this, right? It also takes CPU to compare the v6 addresses compared to the v4 addresses. So it means that most of the firewall doing v6 are slightly less efficient. For instance, on the ASA, we notice something like a drop of performance of 5%, which is okay, right? It's not divided by 2. The other part, which is way more annoying, on some platform, which is purely software, or where the line card can be programmed, that's okay. When your line cards are using TCAM, they got a limited set of bytes they can look ahead. So if your extension at the chain is longer than this, depending upon the platform, the frame is either dropped, permitted, or printed to the CPU. Just remember this, right? It's really heavily depending upon the platform. That's the reason why I give you the tool of SCAPI, so you can test yourself. And I will give you more examples later. One of those extension headers is our friends, fragmentation. Okay? There's an extension header. It's no more the identification and the fragment offsets that were into the IPv4 header are now into the IPv6 fragmentation header. And as we are all in security, we remember that in IPv4, we like fragmentation, right? This can be used to hide, evade, when you can get overlapping fragments, one containing an attack and the other one containing being benign, meaning legit. Maybe the firewall will only look about the last fragment and permit the complete packet, or the firewall and the host will only look at the first one, receiving the attack, or whatever. Very strange combination. That's the reason why IPS system typically has got multiple reassembly to check how the host will do it in all kinds of combination of operating systems. Okay, we know that fragmentation is bad anyway. So, what if we combine fragmentation now with extension header chain? What if we pretend that the extension headers chain is so large that we need to fragment inside this extension header? Look at this. So that was a single TCP segment, but with a hop-by-hop, a routing, and a large destination header. It was too large to fit, or I am an attacker, and I'm using tools to do it. I do it in 2 fragments. The hop-by-hop and routing must be repeated in all the fragments. That's what we call the unfragmentable part of a packet. That makes sense, right? Hop by hop, that's the behavior that each and every router needs to apply to the packet. So to all the fragments, right? Same thing for routing. It's mainly used for doing source routing. So you want to get the 2 fragments following the same path, right? So that's the reason why they're repeated here. Then we have fragment 1 header and fragment 2 header. They will differentiate because the offset will be different, but they will share, of course, the same ID, right? So we can put everything together back. Now, if you are a stateful firewall, easy. You do the reassembly. You are an IPS, easy, you do the reassembly. You are a stateless firewall, an access control list on your router, okay? What do? Okay, I received the first one. Okay, I know the length, I know the length, I know the length. Okay, here I know that the next one will be a destination header. And I know that the length of the destination header is here. And I know that, okay, I can only put so many bytes, so I put the length here. And I say offset 0, okay, because that's the first packet. This one I simply copy and paste, fragment. Here I say the flag more, I put it to 0, because that's the last one. And I say the offset in this packet is, I don't know, let's say 10 or whatever. And the rest. Now, when you receive this one, and you are stateless, you forget about this one. How do you know it's TCP? Because the 6 for TCP was on this very first byte here. How do you know of much bytes I need to skip? Because the length was there. In short, no way to find where the TCP header is. Okay, so basically stateless access control lists do not work in IPv6 world. Come back a bit more on this. Now, of course, by using fragmentation like this, you can bypass device tracking, you can bypass array guard, because they work on a stateless manner. Okay, the only state they keep in the device binding. But the fact that you recognize it's a route advertisement, that's a neighbor solicitation, that's a DHCP, that's on the access control list which are stateless, that are used to burn from the hardware, basically to the CPU. Now, the good thing, that's a kind of a known attack for a couple of years now. The IETF says, at least for NDP, array guard and the like, nodes must ignore NDP if there is a fragment. We cannot process, you should not, you must not process route advertisement, neighbor advertisement, if they are fragmented. And later, this RFC basically merged into 8200. 8200 is the standard now for IPv6, dated 2017. It clearly says, if the first fragment does not include all headers through an upper layer, TCP UDP, then that fragment should be discarded by the endpoint. This one is implemented in all the host operating system. So if somebody fragments a route advertisement to escape a regard, the host will drop it. Okay, so we are safe. Let's have fun with this and Scapy. That's becoming a little bit more tricky on this one. Okay, first, I'm creating a packet, right? The header IPv6, the slash concatenation, remember? I'm creating a destination option header with inside an option, let's say, where I will be repeating 20 times A to make it bigger. Concatenated to a TCP where the destination port is 22 for SSH and the flag is S, like a SYN. Take the big packet. I want to make fragments now. And I will do it easily. Creating the fragment 1. I need to repeat, of course, the header. I'm creating a fragmentation header, telling the next header is 60. 60 is the code for the destination, right? Pretty much like 6 will be for TCP. I create an ID which is easy to recognize, and I say more flag, yes. There are more fragments to come. And the offset equals 0. That's my first byte. Create, and then I concatenate the kind of a strange combination here, that's Python build. I take the bytes from 40 to 48 of the packet I created on the top line. 40, that's the length of the IPv6 header. So basically, I'm taking the first 8 bytes of this extension header. Fragment 2 does the same, basically. I take the rest of the packet, obviously. More equals 0, right? There are no more packets after, no more fragments. Offset equals 1. Offset, like in IPv4, you need to multiply by 8 to get the bytes offset. Okay, and then basically, if you look, for sake of time, I will not do all the thing here, but recognize in the 2 fragments the ABAB, which are the fragment ID, obviously need to be repeated. You see the A, the destination header, is split into 2 fragments, in the first and in the second. And as I said, the 6, explaining that after destination I have TCP, so which is into the destination header, is only in the first fragment. Remember when I was saying that in the 2 on the slide before? We don't see it here. And of course, I put the 16 hexadecimal, which is 22 for SSH, on the second fragment. So basically, you know it's a TCP in the first, and you know it's SSH in the second. So when I did the test, first good news, ASA, poof, block it. And he called it a teardrop. This attack existed, a teardrop attack existed in IPv4 10 or 15 years ago. So they give the same name. Now, if I am using a naive access control list on the router, so Scapy on the left and SSH over here, where I deny port 22 but permit the rest, this guy will receive the 2 fragments, will do a defragmentation, and reply with the sync plus ACK. Yeah, sync plus ACK here. Okay. Thanks God, there is what we call a keyword on multiple iOS version, not on all, sorry, called undetermined transport. Undetermined transport is only applicable to drop packets, that's the bad one. And basically, it drops everything that does not contain TCP or UDP or ICMP, like fragmented. Okay? When the first packet, let's say, does not contain TCP, UDP, or ICMP, like a badly fragmented packet. Works fine, just beware that OSPF v3, RSVP, GRE are not in the list. So if you want to deny undetermined transport, those bad fragments, and you are using GRE, put permit GRE on the top. Okay, just remember this. This sentence here is a little bit more complex, but it's the exact sentence you will find in documentation. But the summary is this. We block bad first fragment. We block also all the rest, right, OSPF, so permit them. Okay, I apply this now on the router in the middle, send the SCAPI, and indeed here, the access control list denied. Okay? Line number 10 is the first one here. On the host, I am not receiving the first fragment, it's been dropped. I do receive the second fragment. After a while, I will stop doing the reassembly, but the session will never occur. Okay? We are protected. So, is it the end of IPv6? Is it the reason why v6 is not deployed or whatever? Not really. It's bad news, right? Don't take me wrong. But you should be able to sleep. Again, it works only for the stateless access control list, so firewalls are not impacted, so at least it's good. We've seen the IETF making change, and as we get more and more updates on the operating systems, the RSE 8200 will also come into being implemented, so the end host will start to drop those packets, so that's good. Undetermined transport is a good way to do it, but not on all the platforms. And remember, some platforms, like using hardware TCAM, has got a limited depth of analysis, right? So they cannot go further, obviously. One thing you may want to do, okay, I cannot drop fragments for any kind of reason. Okay, I cannot deny the TCP SYN on port 22 to my host. But my host will not reply with fragments. It will reply with a normal packet, right? So I cannot block the incoming SYN, but I can block the outgoing SYN plus ACK. So the SSH will not be established. Of course, if somebody is doing a SYN flooding against your server, you are in deep trouble. If you are a stateless UDP receiver, like a syslog receiver, they can flood you. Okay? So it does not apply to all the cases, but think about it. So regarding extension headers, this is basically the proposal that we have, and the IETF and Fernando Gont is working on this. Basically, at the edge of your networks, at your firewall, if you still believe into the perimeter security, obviously, filter out all the extension headers that you don't want. Google, for instance, drop all extension headers at the edge. This may be too strict. Because if you want to do some IPsec tunneling, don't forget AH and ESP are extension headers. So you may want to permit them, either at the router level or in the access control list. But basically, you need to use a white list approach on this. Something else, I don't know if there are service providers in the room. Is there any? Raise your hand. Okay, 3, 4, 5 or 6. I don't know what you do with extension headers, but normally, as service provider in your transit network, you should transmit them as long as they don't harm your infrastructure. Okay? That's up to the customer to protect themselves. At the IETF, there's been a study, and I don't agree because I've done a similar one, and I got different numbers. About 20 to 40% of packets with extension headers are dropped on their path to the internet because some service provider dropped them. I still wonder why. Jan Linkova from Google will redo the study to be presented in Prague in March, and the IETF 104. So hopefully it will be better. Because that's really annoying if service provider drop user traffic, because you cannot extend the internet with this. Anyway, dual stack. Cool, right? It was one of the preferred methods. I mean, now we start to see v6 only network, but not too many. So what are we doing there? One case I've seen quite often. Okay, I've got an IPv4 data center only, like most of us, and you recognize the Linux, Mac, and Windows, and the gray box on the left, whatever operating system it is, wants to get access to v6. So, hey, Mr. Router, assuming that you are connected to the IPv6 internet, please send me route advertisement. And the guy sends, whoops, configure, and by magic, send route advertisement. By default, on Cisco device, when we are sending route advertisement, we are also sending a prefix configure for auto configuration. That's the default. So what you get, here, you got v6, but all the others, because they have IPv6 enabled by default, also have IPv6 access, an address and everything. Now, let's look now at the default protection. The Linux was protected by IPv4 IP tables. The issue is that IP6 table exists for the v6 traffic, but it's not configured by default. So if you have a Linux machine in this case, they are wide open to the internet. Annoying. At least Mac and Windows are better because they do not use IP addresses or TCP ports for defining the policy. They basically say, can this application access to the internet? And whether it's v4 or v6, it doesn't care. And Mac is quite recent. It's a few years only. And when I was presenting this 5 years ago, I was asking, which machine is the most secure? It's not Linux, it was Windows, right? Which was quite unusual, but now it's no more the case. The good way to do it is simply when the gray box asks, hey, I want v6, send me an array. Yes, but I will configure it with an extension called no autoconfig. Then basically I'm sending the route advertisement. So all of those knows there is a v6 router. There's a route advertisement. But none of them can use Slack to get the v6 address. So if the gray box has a static v6 address, then it can go to the internet and only him. I guess you are feeling empty stomach, right? So what about the cookie, even if it's not really for PM or whatever? Session cookies. You remember, in NFTP, there is no real transaction system, so we use cookies. So how does it work? Quick refresh. We have John Doe with an IP address A. We have a server and the database of the server. First login screen, hey, I am John Doe, my password is XYZ. Yeah. The server creates a cookie, that's just a random number, associated into a database if the credential, the password is correct, with the username, whether it has been authenticated, yes, and a shopping cart. And I will explain why sometimes they store the address. And he replies, yes, everything was okay. Here's a new cookie. It is this random number. And the random number is just a pointer in the database for all those information, right? It's stored in what we really call a cookie jar on the browser. So I want to order the good called foo, and here is my cookie that's automated. I look again, is it correct? Yes, and I insert the shopping cart foo. I say, yes, it's been added. I am ordering bar. Here's my cookie again, and blah, blah. Based on this, the only authentication to get access to the shopping cart and the credit card and everything is the cookie. If somebody else steals the cookie, he can simply use it, and the server will be accepting it. Right? It's annoying. That's when we do some cookie stealing. There are basically two ways to steal a cookie. A hostile JavaScript or whatever running on the browser in a separate Windows, obviously, or sniffing if you're not using TLS here. Remember this. So all the applications were checking whether the cookie was really coming from this address A. Okay. Now, what happens if we are using API ball? Remember, that's when we try V6 and V4. Maybe I start over V6, then it's slower, and I move to V4. Or I'm using IPv6 with privacy extension. Remember, the random address. And if you're using an iPhone or an iPad, every time your screen goes black to white again, you get a new IPv6 address. Now you got the point, right? We do these cookies as before. So I start with address A, okay, blah, blah, okay, store the cookie, exactly as before. Now, the user change address, API ball or privacy extension, right? We get more. If you want to add an item foo, it's the right guy, right? The cookie is correct, but the address does not match anymore. And then you are not authorized. And there's a real case. So when you move to a dual stack server, it's not enough to do it at layer 3, security firewall, but beware of this. Okay? And for instance, I was doing it with some banks in Belgium. So that's, Belgium, 2 languages. That's error message. Okay, they are in French and Dutch, but you know something is going wrong, right? You could do it in English, German, or whatever. The thing is that really going wrong. How can we fix this? Simply because we do not need anymore to check the client address. Use TLS. So the cookie cannot be stolen on the path. And use something which is new into when you send the cookie to the browser, use this option in the set cookie header. Secure HTTP only. This will prevent a browser to give access to the cookie to another JavaScript. The cookie will only be used not in JavaScript, but only over HTTP. Okay? Of course, the good user will use a good browser implementing this. And most of them do, so that's okay. An attacker can, of course, cheat, but then he will be cheating with his own station cookie. So cheating with him is not very important. Tunnels. Tunnels are used when you, of course, need to link to a IPv6 island, like this one, on the left and the right, over an IPv4-only network, or vice versa. By the way, we start to see linking IPv4 island over an IPv6-only network. All the tunneling techniques, GRE, ISATAP, 6in4, whatever, have no authentication, no encryption. So basically, if the bad guy knows the IP address of this one, he can generate, let's say, a 6in4 packet, send it over the internet, arrive here, decapsulate it, and inject it. All the packets here are also in the clear. Nothing is new, right? There's the reason why we use IPsec to transport IPv4 over IPv4. So let's do the same thing, use IPsec here. Something interesting. And normally, not a lot of people are using ISATAP anymore. ISATAP was mainly still activated in Windows, by the way. But you need to configure routers that basically will use this prefix to allocate V6 out of this to many IPv4 clients. Okay? And they will advertise this prefix on OSPF, BGP, or whatever. That's basically allowing IPv4-only machine using a tunnel to the data router and then send V6 traffic in it and receive, obviously. Okay, bad guy. The bad guy now knows that there are two ISATAP routers, obviously with different prefixes for different set of clients, let's say Europe and Asia, and two different IPv4 addresses. Now look, it's sending packets to this one, the prefix of the route on the left, and if you look about this address, most of you are not that good in hexadecimal, but you may already see the issue. So, ISATAP receives this one. Oh, that's a v6 packets for my prefix, for one of my clients. So what am I doing? I encapsulate my v6 packet into an IPv4 ISATAP. Destination now, this address. But I'm translating this address, in IPv4. So IPv4 is the same thing as this one. It's just a matter of printing, right? So now, my IPv4 packet traveled to this address, which is the second ISATAP router. Oh, this is one of my clients because the destination IPv4 is mine. Okay, that's one of my clients. When I receive v6 in v4, as an ISATAP, what I'm doing, I decapsulate the v6 packet inside and send it over v6, which is a green packet. And I don't touch the v6 packets, right? I simply decrement the up limit, that's it. This packet and this one are the same. So this will loop. Okay? Of course, there is a hop limit. It will reach 0, and the packet will be discarded, and the loop will stop. So it's well known. There is even an RFC for it. Just to give you an idea, if you have tunnels, because you have to, read this RFC and search for it, okay, because there are variations of this attack. Something interesting before talking to another translation mechanism, which is called MPLS 6PE and 6 VPE. Link local addresses versus global. So together with Michael Beringer, we wrote this RFC, proposing and explaining basically the pros and the cons of using only link local addresses, FE80, on the router-to-router point-to-point links. Why? Because all routing protocol, OSPF, EIGRP, RIP, always relies on link local. You do not need to configure a global address on an interface for OSPF to work. So link local is perfect. One benefit, for instance, is that link local cannot go outside of the link, that's hence the name, but they cannot be reached as well from the outside. So if you use link local in all what you call the P routers, nobody from the outside can send packets to you. Easy protection, right? Rock solid. Now, one drawback is that if you want to reply to a ping or to an SNMP, you cannot reply with a link local. So you need to get a loop back. Okay? Well, there's about 10 pages of the RFC, you may want to read it. What I want to say is it's important that if you go to 6 VPE, which is basically MPLS VPN for v6, that's the big picture here. We know how to secure MPLS VPN. It's there for 15 years ago. The only issue with MPLS VPN, this is this PE router, provider edge, when it's shared among multiple customers, the gray and the green VPN, because if this one is sending thousands of traffic to the shared router, like thousands of OSPF packets, thousands of SSH packets, the CPU of this guy will go very high, breaking as well the connectivity for the gray VPN. Right? This is the only weak point. We can use control plane policing, we can use access control list, a few things like this, but the only weak point of MPLS VPN security. Now, on the PE to CA link, the purple link here, if we use only link local, because typically we don't use OSPF or whatever, right? So only link local. Basically, this interface is unreachable completely from this cloud. And you are securing your PE. Okay? So in this case, that's what I explained here. Again, for for your reading when you are back home. It's basically 6VPE network can be more secure than an IPv4 MPLS VPN, thanks to it. Of course, if you are dual stack, doesn't help that much. Okay? It's only very efficient if you have V6 only. Okay. So we have, yes? You don't want? Probably somebody else.
And then I'm dropped. Then second level is then debugging. They are saying, yeah, it's from the operational perspective very bad.
That's correct. So to summarize, it's more like a command rather than a question, I think, that you say that using link local as well makes operation much more tricky, much more difficult. That's obvious. Okay? That's when you read the RFC that we wrote with Michael, we say it again and again. The beauty if it's very secure. You need to put it to balance. And again, the only sensible way of using it is between the PE and the CE. Because there, that's really where you do not need so much of management and operation. And then that's a high exposure. That's a high target. You don't want them? Sorry. Sending two at the same shot is not good either. Okay, sorry about that. So telemetry. So we have deployed all those tools, but we want to feel what's happening in my network. And we may want to use the same system as in IPv4, like SNMP that exists, or NetFlow that exists as well. The only thing to know in SNMP, whether you want to look at IP or routing, there was a MIB for the IPv4 only, and there are other MIBs that are valid for IPv4 and V6, but they are different. So you will need to change the MIB entries in the OID that you are using. For instance, on this one, I was using SNMP work, an easy utility, just to get all the mapping between the IP address and the layer address. So the ARP cache and the NDP cache. And in the same shot, I got all my V4 addresses with the MAC address, and all my V6 addresses and their MAC address. So very interesting to download and get access to all the cache, V4 and V6. The tool doesn't understand how to decode the V6 address yet. There's a reason why it's displayed a little bit strange. NetFlow. Specifically, if you go to NetFlow v9 or flexible NetFlow, you can have a huge amount of information. That's with flexible NetFlow, that's all the information you can get about an existing flow. And one which is I love is extension. That's a bit mask. When you are putting a flow, for all packets in the flow, is making basically setting bits as soon as receive, for instance, a routing header or a hop by hop or a fragment. So it allows you easy to see which kind of fragment of extension headers I use in your network. Remember I said whitelist approach at the edge? That's an easier way to do it than using a sniffer and passing in all the packets, right? Way easier. And typically, routing header, if you don't use segment routing, you should see 0. Else, somebody is trying to use source routing or making dirty tricks. So that's really, really useful thing. Simply, again, the blue booklet, that's how to configure NetFlow, but we are not in an NMS, we are in security. One thing as well where I do love NetFlow. Remember what I said when we were scanning a network with V6? It's painful for the router because you need to do so much neighbor solicitation. Beside decision guard, there are also limits. So all the iOS routers basically only allows for 256 incomplete entries per interface. So basically it's bad. It prevents you to scan. And also if you want to scan a network in IPv6, it will take thousands of years, right, for enumerating all the addresses. So basically you cannot scan your network. It's not a security feature, because anyway, the attacker will find you. But now, who is scanning your network every night? InfoSec, right? Because they want to discover whether there is a new device, a new host, a new switch, a new access point in my network, to make an inventory. How can you do this in IPv6? It will take 50,000 years. No way. So I'm proposing here to use NetFlow to simply collect all the IPv6 addresses that are used in your network. And then you can get your inventory there. Another way of doing it, but it needs a link local access, is a link local multicast for all nodes. So if you do this ping with the right parameters, you will receive echo reply from all hosts in this LAN. But it's link local, okay? You need to be attached to it. So if you do a scanning, you need to be on the same VLAN. You cannot send it across as a link local. Talking about vulnerability scanning now. So I know I got my inventory of machine. How do I scan all the ports to see whether it's a web server, which is the version of Apache, the version of Nginx, or whatever? As soon as you are dual stack, you need to do it over IPv4 and IPv6 and check whether they are the same. If one port is open in IPv6 and not in IPv4, maybe it is on purpose, then it's okay. Or maybe it is, you forget about the access control list somewhere. And even worse, you need to scan to the link local address. Think about a shared data center where you can have hostile parties in your data center, or maybe a compromised machine. This compromised machine sits on the same LAN as other VMs. It can use link local to connect, even if there is no v6 traffic, right? Again, remember, what defines a v6 network is v6 operating systems. So it can use link local to attack another machine. Even if you use IP tables, deny any, it will go over v6. Again, kind of a bad news, but okay, that's life. Yeah, that's basically the pen test. Your question was about penetration testing, and indeed that makes penetration testing much more complex here. Because you really need, if you want to do it correctly, you need to go in each and every VLAN of your network to do it. Or extend the VLAN back to your data center or whatever. Yeah, not easy. Ready? Oops, the other one. Fragmenting socket is better than sending two fragments in the same shot. So forensic, in this case, I have a v6 address. I know it's badly behaving. I want to know what's this. I need to find it back. First thing, a v6 address can be written multiple ways, right? Uppercase, lowercase, leading zeros, not compression. So you cannot use grab or find command into a configuration file or a log, because depending upon the program, depending upon the operating system, they will be displayed slightly differently. Annoying. The other part is that if you are trying to look about, okay, I got a connection to this host and another one from this host to another one, like using the first host like stepping stone. How can you make correlation if the first connection was IPv4 and the other one was IPv6? How can you stitch this together? Okay? Not so easy. There are, SIM can do it, but when you look for a security incident event management system, you really need to think about it. Regarding the multiple ways, to write the address, I wrote this small Perl script that basically takes any file, looks for all the v6 address, and basically dump them with all the rest in the same format. I mean, it took me 5 minutes. We can redo it as well. Now, using EU64, normally nobody's using it except printers maybe, all IoT world. EU64, you take your 48-bit MAC address, right, this one, and you insert FFFE in the middle, and that's it. You can do the reverse, right? If you see FFFE in the middle, that's most probably EU64. You remove this, you glue together, you need to flip one bit, and that's it. And once you have the MAC address, you know how to find it, right? The CAM table on the switch, and you know which VLAN and everything, which port. Now, another, I would say, bad news is that, oh, Eric, but when I have an IPv4 address, I look in my DHCPv4 list, and I know the MAC address, the client ID. Not so much in V6. The list of an IPv6 address in IPv6 is not to a MAC address, it's to a unique DHCP unique ID, DUID. Sometimes that's a MAC. It depends upon the client. Sometimes that's the MAC plus a timestamp. Sometimes it's a random number. So for instance, in this case, I look in my DHCP binding on my server, and indeed, the MAC address was there, and I can double check quickly, because the link local address was indeed as well, the link local, EU64, and you recognize the 7548. Okay? Yay! I got back my MAC address. Issue. Android phones do not support Android, and they don't support DHCP-v6. So you need to use Slack and no more DHCP. Other point, look at this as my home. There's the laptop of my wife. There is indeed a MAC address of her laptop, but the MAC address she was using over wireless was this one, which is not that one. That one is her Ethernet adapter MAC address. Don't forget, it's a DHCP unique ID. You have a unique ID for all your interface, right? Bluetooth, Ethernet, or whatever, Thunderbolt, a unique ID. In the database or the list, you will always see the same DUID with sometimes a MAC address, but not always the MAC address which is being used. Not really good, right? Radius accounting. Now, if you're using WPA, you can enable radius accounting. It's typically not visible into the GUI, because it's very specific. You need to do it by the CLI, but who cares? And in this case, you get accounting, meaning, hey, new IPv6 address or new IPv4 address, and the name. And it's locked. So you get everything in the same shot. Do not need to find the MAC address anymore, because you get the name directly. So, you've seen why, I'm giving you bad news, right? Because that's how you need to be aware. If those previous techniques do not work, let's be stupid and do the stupid thing, but efficient thing. Let's collect by SNMP every 5 minutes the content of all my neighbor cache in the old routers of my network and store it into a SQL database. Is it smart? No. Is it painful somehow? Yes. Is it beautiful? No. Does it work? Yes. And that's what you want, right? One way of doing it. Another thing is that if you're using device tracking, you can issue a syslog every time you learn a new binding. Remember the binding table for device tracking? Every time in your new binding, you can have a syslog. So that's good. Security policies. So we secure at layer 2, layer 3. How can we enforce the security policy? So let's start with the firewall. Still talking about the ASA, because we supported IPv6 14 years ago. And then we keep improving. We are not yet there, in my humble opinion, and specifically what I would love is that we can block specific extension headers, we can block if they are invalid combination, and so on. So This one is really nice. And I will talk a bit later, mixed mode object. And somehow recently we had to move to the support of RFC 8200, so the new IPv6 standards, because it has a minor difference on the way it handles, a packet with incoming hop limit equals zeros for you. Hop limit 0 for a router, you drop it, because you cannot forward and get -1, right? That's clear. But it was unclear in the previous definition, specification of V6, what happens if I receive for me a packet with hop limit equals 0? So AZ was blocking it, paranoid. No, we need to change it and allow it, because 8200. With a nice side effect that there are some CMTS, so that's the router of the cable modems, right? They were sending DHCP PD, prefix delegation, so to get the addressing inside your home, with a hop limit equals 0, which is stupid, right? Because typically you send those things with hop limit 255 to see whether it has been routed, yes or no. But anyway, it was sent by 0. So we fixed this bug. And this is how prefix delegation is done, pretty much like in iOS. When you declare the client, you see the prefix delegation is this name, this general prefix, and on the inside, on all the interface, you use this prefix and you add the right-hand side. Simply to it. So you can use prefix ::1, prefix :2, and so on. So if you receive a /48 from your provider, like hint over there, you can have 65,000 interface on the inside with all of them a different prefix, a different /64. This is really cool. But if you change the prefix, you need to change all the access control list. Okay? There's a reason why I put it in red, because I'm not happy at all. We should be able to use those names in a group, in an object, a network object. It's not yet the case. Regarding the extension headers on 5 power, it's not visible on the GUI. You need to use flex config and go like this to achieve the same thing as the ASA. But it can do it. Okay? It's working. Mixed object. And that's important, because you need to have the security policy for IPv4 and IPv6 identical, right? If they block a port, must be blocked on v4 and v6. If they allow a port, must be allowed in v4 and v6. Except exception, right? Don't take me wrong. So in a single line, single GUI, you can have a mix and match of v4 addresses and v6 addresses. It's not the case on routers, for instance, because you get a v4 access control list of 1,000 lines and another 1,000 lines of IPv6 access control list. And how can you check if it's the same? You cannot really. And the same thing, you can have basically network objects, in this case containing addresses which are v4 and v6, which is quite cool. Spam. There's an actual spam I received 2 years ago, 3 years ago even, on my own server. And you see, yes, it was sent from a v6 address, from a provider in Germany, but most probably an open relay. Oh, honestly, I'm receiving, so the question is, how did I get this? I mean, the message itself, I had to go through 1 year, roughly, of email, because I don't receive so many emails to my private email, to find something that looks like a v6 address, and then it's basically a WHOIS to find exactly what it is. Yeah, I don't receive so many of them, to be honest. Notably because if you want to send an email to Google, you need to get all your DMARC and your SPF and reverse completely set. So it's typically the email you receive with v6 are usually much strict regarding authentication. Anyway, so if you go to Talos to see what is the status for a v6 address, first I got a small header on here that tells you, yeah, I got to the website of Talos of a v6. Okay, I got indeed a v6 address that so I can look for. something I'm not too happy as well, location data 0. While MaxMind, there's a free geolocation database that can give you the city as it, so I don't know why. And we have not so much reputation yet, but it supports v6. The only thing is, you know, the reputation is built up by yourself using the system. So quick summary of the Cisco v6 product. Not everything is there. What I don't like, of course, what is in red. For instance, Cisco Umbrella. They can reply if you ask, they can reply over v6, okay? So you can put v6 at the server for Umbrella. They will answer with a quad A, but they cannot assign a specific policy to your own v6 address. So if you have dual stack at home, let's say you want to prevent access to porn for your kids, if the website is IPv4, it will be blocked. If the website is, if your kid is smart enough to ask the DNS over v6, it will not be blocked because we cannot apply policies there. VPNs. And VPNs are, of course, important. I put here two cases. One is side-to-side, so from one branch to another branch, remote access. This is what you are doing when you are here on the hotel. And whether the open network is IPv4 or IPv6. We've got answers and products everywhere. Okay. Remote access, AnyConnect. And by the way, not everyone can have this. For instance, there's a blocking factors for some people that want to offer IPv6 only captive portals, because it's easier for them. I mean, everything works over v6 except some SSL VPN from some vendors. So you cannot VPN in IPv6 only. So if you connect here, for instance, on Cisco Live NAT64, which is v6 only, plus NAT64, using my AnyConnect, I can go through. If you are not using AnyConnect, you should try it. Maybe it will be working, but I really encourage you to test it. Talking about site-to-site, the old solution was DMVPN, still working, of course, and I put in green what you need to change compared to IPv4. The main differences, or the only differences, are v6 rather than v4, and of course some v6 addresses at some point of time. If you build one tunnel like this, inside the DMVPN, you can send IPv4 and IPv6 packets. You can make a dual stack tunnel. And it can run over IPv4 or IPv6. And I heard about a customer in US that was able to negotiate with his service provider an IPv6 only CPE. So the service provider did not give to the CPE any IPv4 address. And they were building a DMVPN over the thousands of branches over IPv6. And funny enough, inside the DMVPN, it was IPv4 only. But if it was cheaper, this may be $1 a month times 1 or 2,000 CPE, why not? That's kind of smart. The new solution for doing hub and spoke site-to-site is what we call a FlexVPN. And again here, the major difference is IPv6 tier rather than IPv4. And again, it runs over v4 or over v6, and inside it can be IPv4, v6, or both. As I said, AnyConnect works fine, specifically on a laptop, not always on all the mobile phones. And the addend is ASA. Again, v4, v6, inside, outside, we don't care. It's becoming pretty flexible here. Talking about VPN, and I understand it's close to lunchtime and your brain is possibly melting. Think about it. Big difference between v4 and v6 is that in v6 we have global addresses. the address you receive from your service provider or from RIPE are global. The inside address of your clients, PC clients, on the data center will be global addresses, not network 10. Those global addresses are routable over the internet. Normal case, FlexVPN, I am a client in a branch. I want to reach a VM in my data center. I am routed, obviously, to the CP in the branch. I jump into the DMVPN tunnel because I'm running routing between those machines, participating in DMVPN. I exit DMVPN and go to my VM and vice versa. If you are naive and your DMVPN is down, the tunnel is not there, client still want to go to the same VM, route it to the CPE, and if you are announcing the prefix of the data center over BGP, packets will travel in the clear over the internet, right? Because it's a global address. Reach the router at destination, will be routed to the VM. So that's what I explained here. So not a big deal. You need to understand it. You need to be sure to inject on BGP or to the external world only the strictest, the smallest prefix. And you need to ensure at the edge, if I'm receiving clear text packets that should become only via the encrypted tunnel, drop. Okay? Kind of simple, but just beware of this. Regarding, yes? So the gentleman points, is asking a question, but you know the answer, I'm pretty sure. So and let's take the case of Cisco. We have a /32 that we apply everywhere. Okay, so all the branches, all the offices are using this /32. Now, in some case, when we receive, let's say in a branch of Brussels, where I'm based, we receive from the internet connectivity, V4 and V6, and we get a prefix, of course, from the service provider. If we use a tunnel and we use the MVPN, I will not use the address of the provider in my branch. I will use the /32. To the extreme, most of the Cisco employees has got what Cisco Virtual Office, which is a small DMVPN router at home. I got it. I got a V6 address, /48 from my provider. I distribute it to my kids and my family over Wi-Fi on one SSID. Another SSID is reserved for any Cisco colleague and myself coming. I am using a 2420, which is a /64 out of the /32 from Cisco, even if I'm receiving a /48. So my wife has got something, I don't remember the prefix, and I got a completely different prefix. Okay, printing is a little bit annoying in this, right? The printer is on the other side, but that's a different story. So that's a good point. The largest IPsec deployment is most probably this one, BC Hydro, British Columbia, northwest of Canada, Vancouver. They are using an IoT deployment with a mesh networking, and they've got millions of devices using IPv6 only, using a routing protocol called Ripple, and using IPsec to secure all the transfer. Look about this session is not this year, but it was presented last year. So look it on Cisco Live online. And the language engineer that worked on this, Rob Barton, is here. So we can maybe ask this afternoon a MIDI engineer with it. So summary. Key takeaway. I didn't spend time with you explaining that 98% are identical between V4 and V6. A few things are different, like the line layer, but we've got the same thing as apps, dynamic app inspection and DHCP snooping, called first stop security. Big difference are the extension headers. So again, it should not be a blocking factor. Look about all the slide and my guidelines, you should be okay. If you want to test device to check whether you remember the access control list with extension headers, how deep your device is going, SCAPI can be a good tool. Okay? Because it's enough to send one packet, it's okay, it's not a performance issue. I repeat myself, but training is required. Okay? You have been there, so you learn a little bit more, I hope, regarding V6 security. But what about your colleagues? Remember, V6 is already in your network because you have Windows, you have Linux, or whatever. They need to know about IPv6 security. Recommended reading? Lack of modesty of mine, but I wrote 10 years ago a book with Scott about IPv6 security. It touched Windows, it touched Linux, it touched macOS. A few things are not there, notably all the fragmentation issue, but it's still very valid. You can download it, because I don't think they are printed anymore. Another one, most of the content I just explained today is also into an IETF draft that I am authoring with a few other people. And KK works currently in WeWork, but before he was at Google and before he was at Dropbox. So he knows how to run the network. And the two other ones are basically security consultant people. And all the RFCE and IETF draft are free, of course. As I said, WebEx team is open. Obviously, I cannot be there. Survey. Beside my role here as a speaker, I am also trying to coordinate all the IPv6 sessions. Okay? All the IPv6 sessions I've reviewed mostly each and every slide, trying to avoid overlap. That's the reason why I said at the beginning here, there is overlap with this session. It's important to get your feedback, honestly. So put good scores, or best score, whatever you want, preferably good score, obviously. But the comments for this session or for any other session in the Cisco Live, put comments, suggestions, what was good, what was not good, what you want to see. We read all of them multiple times. They are compiled in list, it's anonymous, by the way. I don't know who said what. Okay, nobody knows. So do it, but we really love to get your comment there. We are mostly done here because there's only one day left. There are the remaining V6 sessions, including labs. You may want to go. And the list is complete, so you can get access to the archive when we are done. Besides this, I would love to thank you, and I hope you will get a nice lunch. If you want some chocolate as a dessert, the box is here. You are free to come and collect. Thank you.